If you're into audio, you've probably run into this at some point. You can have a very capable DAC, amplifier, and speakers, but the room still dominates what you hear. Bass is uneven, imaging isn't stable, and the soundstage never quite locks in. Until now, room correction meant compromise. Pay a premium for a closed-box algorithm, or rely on basic EQ that introduces phase smear and destroys your transient response. That ends today. Welcome to GSonic Reference. This is a completely free, mathematically flawless DSP tool that changes the game. Without the typical steep learning curve, GSonic measures your room and generates high-resolution FIR correction filters. You get sub-second latency and a level of precision that is already beating the industry's best-paid tools in early testing. Today, I'm going to show you how to bypass the compromises, measure your system, and generate your own professional filters in under 5 minutes. Let's dive in. You'll land on this GSonic GitHub repository when you click the link in the video description. Here you can find all the related information about each update, including what has changed, what's been fixed, and other details. Typically, you'll want to go to download latest release. Here, depending on your platform, whether it's Windows, newer macOS, older Intel-based Macs, or Linux, you need to download the correct file. Since I'm on Windows, I'll download the Windows zip file. Keep in mind, this version number will likely have changed by the time you watch this. Let's save it to the desktop as we always do. Once the zip file is downloaded, extract it. You don't have to extract it to your desktop. You can save it wherever you prefer to use it. Now, here is the app, GSonic Reference. On Windows, you should right-click the app, go to Properties and check Unlock to prevent security pop-ups. Then, double-click to start the app. The interface has two main tabs, Measure and Generate. The Measure tab is where you take your measurements, and the Generate tab is where you create your filters. There is also a Help tab, which contains all the instructions you need to use this app. It's very straightforward. Finally, the About tab contains copyright and version information. When you're in the Measure tab on Windows, you generally have to choose between ASIO or Wasapi drivers. ASIO offers lower latency, but Wasapi is much more compatible. On Windows, ASIO is restricted to using a single audio interface and driver at a time. If you have an audio interface, it typically comes with its own ASIO driver, allowing you to choose the input and output on that same device. However, you can't normally combine two different ASIO drivers for input and output. While there are routing tools that handle this properly, like VB Audio Matrix or the discontinued ASIO Link Pro, I don't recommend using wrappers like
ASIO for all
or Flex.
ASIO.
They are essentially just
Wasapi
wrappers, and they often introduce more latency than native
Wasapi
drivers would on their own. Fortunately, you don't need ultra-low latency for this app. You're just taking one-off measurements, so speed isn't critical. People usually prefer ASIO on a single interface to avoid clock drift between different devices. However, GSonic Reference plays chirps at the beginning and end of the sweeps to calculate and compensate for clock drift very efficiently. Because of this, Wasapi drivers work perfectly well. Also, if you're using a USB mic, you have to use
Wasapi
since they rarely come with
ASIO.
Even if they did, you'd still need a separate ASIO driver for your output, which creates a conflict. Keep in mind, this is all specific to Windows. On Macs, you simply use Core Audio, and on Linux, it's ALSA. Audio routing is much simpler on non-Windows platforms. Since I'm using a
Motu
interface, I'm going to select
Motu
Gen 5 as my ASIO driver. My speakers are currently connected via an optical cable to my amplifier. The microphone is plugged into line-in 1 with 48-volt phantom power turned on, and all other settings are configured correctly on the
Motu.
I'm using a 48 kHz sample rate across the board. Next, you'll configure your mic. First, choose the output folder where your measurements will be saved. I'll save mine in the same folder as the app. Next, I'm going to load the calibration file for my Earthworks measurement microphone. I'll navigate to Documents, then Mic Calibration. I'm selecting the horizontal forward-pointing calibration file. I prefer not to use the 90-degree files because they are often generic, and I don't entirely trust their high-frequency accuracy. Furthermore, microphone capsules are usually more sensitive and accurate when pointed directly at the speaker. Pointing forward from the center, listening position creates an equal angle to both speaker tweeters. While the left and right measurement positions introduce a slight angle compromise, that compromise is identical for both speakers. In my opinion, this yields the best results. Of course, you are free to use a 90-degree calibration file and point the mic straight up if you prefer. The app can automatically recognize most calibration files. I'll double-click this one and now it's loaded. Finally, we have the test sound section. Here you'll play a 3-second burst of white noise through your speakers. You should set this to the volume you normally use when listening to your system. Let's play the noise. Okay, you can see the peak and
RMS
levels right here.
The output level should be equal to the level you listen to your music in your system regularly. And if you see a warning here that level is too low, then you have to increase the volume, so somewhere in between. Now that everything is working, input-output channels are correct, you selected ASI driver, time to start measuring. The microphone is horizontally placed in the central main listening position, ideally between left and right speakers, at ear height, and I'm starting. So you hear the two chirps at the beginning and end of each sweep. That helps to correct clock drifts between other interfaces. It typically measures left speaker and then right speaker at each microphone position. It measured for the first position and now waiting for us to click continue to measure the next position. So I go and move the mic about 20-25 centimeters, maybe longer, to the right, still pointing forward towards the front wall, and remeasure. Left finished. Now second position also finished. You can see the clock adjustments done here and the measurement levels. Now I move the microphone to the right of the main listening position about 25-30 centimeters and remeasure the last position. So now all three measurements are complete. That's all you need to do for measuring your system. And it's time to move to Generate tab to create the filters. Here you can select an output folder. You can select which measurements you want to use. Let's typically browse to, and each measurement with a time and date stamp creates its own folder. So our measurements are under this folder now. Select that one. An output folder, unless you select one, the filters will be saved in the same folder as the measurements, however you prefer. Let's keep it at default. And you can give names to the filters depending on the microphone position, distances, and volume levels, etc. But I will leave it empty. And target curve on auto, this is a typically -1 dB per octave fixed tilt from the low frequencies to the high frequencies. The tilt angle depends on the room size, really, but this works with mid-sized rooms quite well. I mean, I prefer this to other target curves in the folder in my specific setup. Acoustics default comes from A1 Acoustics. A lot of people love this one. It's here by accident, in fact, but it's a nice curve, a bit bass heavy for my taste for music. The others are standard curves that a lot of people are familiar with. And you can also create your own target curve. Just make sure you save it here. Let's show you the app folder first. Here, target curves. If you just save it as a text file here, but make sure there is no bass roll-off in the target curve. So curve goes flat all the way to 2-3 Hertz. You should not let it roll off about 25-30 Hertz like with some curves. Dolby Atmos Music curve, for example, has this slope already embedded in it. That will confuse the algorithm. So use a flat curve. There's also a warning here about it. Here, custom curves should not contain bass roll-off. I'll keep using in the auto, so you don't even have to select the target curve and just click Generate Filters. As you can see, it already found the perfect roll-off frequencies of your speakers and processing filters now. The code is pure C++. It is still taking time, so a lot is going on behind the scenes. Every filter is created. You're done with that. We can even close it now. And now let's see what came out. So these are the measurements. 3 positions for front left and 3 positions for front right. And these are the filters. I should have saved them in a different folder. Bypass filters only have the gain match with the actual filters. This is purely for AVX listening comparison, because volume differences can be deceiving when comparing filters. So these are at the same volume, which means it dims down the volume as much as the actual filters do, because actual filters have their clipping protection embedded in them very precisely. So you don't need to use any headroom management in your convolution engine. These give the system the same volume. Otherwise, because when you remove the convolution filters, the volume is suddenly gonna increase, which you might perceive as better sound. It is not. So these help you to compare the filter from no filter version of your sound. And typically you don't need them. What you need here is this one. For most convolution engines like Roon can use this, JRiver can use this directly. Equalizer APO and HQ player convolution engines, they both need left and right filters separately, and probably a configuration file. With Equalizer APO, it's easier. I don't know really how to do it in HQ Player, but I know from user experiences that they need separate left and right filters. These filters do not embed information in them that they are for left or they are for right. They need a configuration of some sort to tell the convolution engine channels they belong to. This one, however, has the information already in it. Let me just show you how to use them in Roon. I had to move over to this PC. Okay, here you go to Muse, which is Roon DSP engine. And you don't need headroom management. You can keep it open just to see clipping if you want with 0 and show clipping indicator. But that is extra processing, so you really don't need. The filters are very safely removing any clipping potential. Sample rate conversion, you don't need to as well, but I do. Now the filters are at 48K Hertz sampling rate, but Roon, for example, will automatically resample them with whatever you play, including the SD files, so you don't have to deal with any of that. And here you add filter and convolution, and it's enabled, and then you browse and go to where your newly generated filter is, which is under here. And so this one, stereo filter wave. You don't need to zip it, you don't need separate files, just this one. And that's it. Now the filter is playing. And if you turn it off, much higher volume. So that is why you, for example, say this one is stereo bypass. Say this as flat. So now you can instantly switch from flat to GSonic. They're obviously listening from my PC speakers with filters made for my stereo speakers. Don't make a very useful difference, but just to show you how that will work. Now, if you're a JRiver user, I also have that one, quite similar. In JRiver, you go to the DSP Studio, convolution, you tick this, and here browse to the stereo file again, this one. You don't need to normalize, they're normalized already. Automatically switch filter based on input format, that is useful, and that's it, done. For Equalizer APO, I will leave a link in the video description to this YouTube video tutorial for Equalizer APO for Windows only. This is a very nice tutorial from Elite Designs, and he has really explained it in a very easy to understand format, and program itself is very easy to use. You just select channels and direct it to the convolution file. The only thing I remember from Equalizer APO is that you have to save the wave files inside the config folder where the app is installed, and the rest you just do from the screen, very easy. Plus and minus you add and remove, and you have to use separately left and right filters, which are saved for you in the filters folder by GSonic Reference. Is there anything I forgot to say? Okay, for audio video receiver users, make sure you disable any extra filtering on your left and right front channels, set them to large full range, and reset their distance delay settings to default. Many amplifiers have a pure audio mode. I think that would be the most suitable for measurement and playback because your filters now are in the computer. And if you don't have a calibration mic and if you own an Audyssey microphone, check the link in the video description. I have included a generic Audyssey calibration file that works with GSonic. And that's really all there is to it. With these steps, you'll be up and running with excellent results in no time. A premium version is in the works. The only way to surpass what this version delivers is by adding active room mode dip cancellation to the bass response. But that requires complex multiple input, multiple output filters and specialized algorithms to create properly. As far as I know, nothing like this exists on the market yet, and I believe it's the future of DSP. Premium version will also support custom calibrated Audyssey mics, so if you already have one, don't invest in a new calibration mic. That's it for this one. Thanks for watching and enjoy your upgraded sound.